We've all seen it, that incredible, quiet blanket of white that just completely transforms the world. But if you ever really stop to think about it, that tiny six-sided star that lands on your mitten, it's like a perfect little autobiography of its entire journey, all the way from the clouds down to you.
I mean, just look at them. Every single one is a fleeting masterpiece. They're so intricate, so symmetrical, and just impossibly delicate. It's like nature is crafting these little tiny jewels out of nothing more than frozen water.
So that's the real question, isn't it? How does something as basic as water vapor end up creating this kind of complex, beautiful art? Well, the secret actually lies deep inside the water molecule itself. To really get what's going on, we have to start at the very beginning. We're going to look at snow's secret blueprint, which all starts at the molecular level. Okay, right off the bat, let's just clear something up, because a lot of people get this wrong. Snow is not, I repeat, not a frozen raindrop. What you're thinking of is sleet. Snow is something way, way more interesting. See, the process is actually much cooler. Way up in the clouds, where it's super cold, you've got water vapor. That's just water in its gas form. Well, it finds a microscopic particle, like a speck of dust or pollen, and it freezes directly onto it. It completely skips the whole liquid water phase. And here it is. This is the secret sauce. When water molecules freeze, they don't just clump together randomly. They lock into place in a beautiful hexagonal lattice. This six-sided structure is the fundamental blueprint for every single snowflake, and it's the reason they almost always have six sides. Okay, so we've got our basic six-sided crystal seed. But how does that little hexagon turn into a unique, complex masterpiece? Well, this is where the atmosphere itself steps in and becomes the sculptor. I absolutely love this idea. You really can think of every single snowflake as telling the story of its fall to Earth. Its final shape is a perfect, frozen record of all the different temperatures and humidity levels it traveled through on its way down. And this is where things get really wild. Just look at this chart. A change of only a few degrees can completely flip the shape of a growing snowflake. At around -2°C, you get these flat, plate-like crystals. But drop it just a bit to -5, and bam! Suddenly it's growing these long, thin needles. Then get this, at -15, it switches back to growing flat plates again. It's this bizarre little dance between temperature and shape. But temperature is only half the story. The other huge factor is humidity. Basically, the more water vapor there is in the air, the faster the crystal can grow. And that fast growth is what gives us those beautiful, intricate, branching arms that turn a simple little plate into a stunning stellar dendrite. You know, the classic snowflake shape we all draw as kids. So when you start combining all these shifting temperatures and changing humidities, you get an absolutely stunning, almost endless variety of crystal shapes. Let's check out a few. This slide just shows it perfectly. On the left, you've got a crystal that maybe tumbled through a dry zone at around -5 degrees. It becomes a simple, sharp needle. But on the right, a crystal that fell through a moist cloud layer at -15 degrees just blossoms into this gorgeous, complex dendrite. Same building blocks, totally different journeys. And the family tree is just incredible. Scientists have identified all these different types. You've got your basic prisms and needles, sure. But then you get these incredible sectored plates that look like starbursts, and of course the stellar dendrites, and then you get the really exotic stuff, like capped columns that look like tiny spaceships, or even 12-sided crystals that form when two snowflakes actually collide in midair and fuse together. But, the story doesn't end when the snowflake hits the ground. Oh no. In fact, that's when a whole new set of fascinating physics comes into play, and it affects our world in ways you might not even realize. Think about this for a second. Have you ever noticed that? Right after a really heavy, fresh snowfall, the whole world just seems to fall silent? Well, there's a really clear physical reason for that. It's all about acoustics. See, a fresh blanket of snow is mostly empty space, just tons of tiny air pockets trapped between all those fluffy ice crystals. That structure is a fantastic natural sound insulator. It literally absorbs sound waves, making everything quieter. It's like the world just got a giant, fluffy, soundproofing blanket. All right, here's another one you've definitely experienced. What about that sound? You know the one, that incredibly satisfying crunch when you walk on really cold snow. What is actually making that noise? Well, that sound is actually the sound of millions of tiny ice crystals breaking and grinding against each other under your weight. It's a chorus of microscopic fractures. And here's a fun fact. The colder it is, the more brittle those crystals are, and the louder that crunch is going to be. Now, get ready for this, because this is probably one of the weirdest and most important ideas in all of snow physics. Even when it's well below freezing, the surface of an ice crystal isn't totally solid. It's covered in this microscopic, invisible layer of water that's not quite liquid and not quite solid. It's called the quasi-liquid layer.
And this little layer is the secret ingredient for, well, almost everything. It's the reason ice is slippery. And it's also the reason snow is sticky enough to pack. When you squeeze a snowball, the pressure melts the crystals just a tiny bit. And this liquid-like layer helps them all refreeze and bond together into a perfect sphere.
Okay, and finally, why is snow white? Well, it's all about how light bounces around. When sunlight hits a snowbank, it gets scattered by all those countless ice crystals. Pretty much all the colors of light get reflected back to our eyes, which our brain sees as white. But have you ever looked into deep snow, like in a hole you dug, and noticed it looks blue? That's because as light travels deeper into the snow, the ice absorbs more of the red light, so the light that makes it back out has a beautiful blue tint.
So, from a single water molecule all the way up to a vast, silent, blue-tinged landscape, the physics of snow is just this remarkable journey.
And just when you think you've got it all figured out, let me leave you with one last mind-blower. While most snowflakes are pretty tiny, under the absolute perfect conditions, they can actually form massive structures up to 2 inches across. Can you imagine a 2-inch star made of ice just floating down from the sky?
You know, it's really hard to say it any better than Henry David Thoreau did. How full of the creative genius is the air. It's just beautiful. So the next time it snows, I hope you'll take a second to look really close. Because you're not just seeing frozen water, you're seeing the amazing result of physics playing the role of an artist, literally crafting stars right out of the air.